Okay, so this question asks us to find the magnitude of the resultant force of all of these different charges as they sort of affect point A in this little cube. We know that each point has a charge of Q, and all of the distances, or all of the direct distances are S. So let's start off with the easy answers, or the easy vectors to find. So if we look at point D, this is at 0, S, S. So that's the position of this. So its x component is 0, y component is s, z component is s. And then if we look at point A, we know that A is going to be s, 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 right? And it's sort of recurring theme, but you can sort of tell if you look at it, all the distances are s. So what we can do is we can write this as a position vector. So the position vector would be s I hat plus 0 j hat plus 0 k hat. And how we got this is just from D to A, it moves from 0 to S, so that's S. From S to S is no movement, from S to S is no movement. That's sort of how I picture it in my mind. Then what we need is the magnitude of dA. And what we're going to find with this magnitude is this is going to be the distance formula that this is going to be the distance when we plug it into our charge equation, our Coulomb's law equation. So it's going to be the square root of s squared plus 0 squared plus 0 squared. Very easy to compute. This is just s, right? And this we'll see is going to be equal to our r value. But then one more thing we need is we need our direction. And for our direction, we're going to find a unit vector for dA, which is going to be, to calculate the unit vector over the magnitude is going to be equal to, so s I hat over s, right? We don't need to write the zeros again, which is just going to be I hat, which makes a lot of sense because if we look at this, this vector is only acting parallel to the x-axis, which makes a lot of sense that our answer is only I hat. It's only acting on the x-axis. So now we just need to put it all together. Recall our forces KE, Q1, Q2 over R squared. That's our force from the charge. So this is going to be KE, and Q1 and Q2 are the same because each of them has the same charge. So Q squared. And then as I said, R squared is the distance between them, which is the magnitude of the position. So it's just going to be S squared. And then we just have to worry about the direction, which in this case is just I hat. And don't need to repeat my work. If we look at from B on A, and this is F of D on A, the vector F of D on A. So if we look at F on B on A, it's going to be exactly the same, except it's going to be acting in parallel to the z-axis. So F of B on A vector is KEQ squared over S squared, but it's acting on the z direction. Okay. Again, same with F, right? F of F on A, the vector KEQ squared over S squared, J hat, right? And we could go over and do this again if we needed to, but if you look at F, right, this is going to be at point, S, 0, S, and then A is S, 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 and you can sort of see the similarity between that and D of A. And we're going to end up with the same answer because it's all just in one axis. Now we have these three vectors, but we still have a handful more to do. So what we're going to do now is we're going to look at E. So if I change color here and then go F of E on A, right, this is what we're looking for, the vector. First, let's find E. This is going to be at point 0 in the x direction, and if we look, it's going to be 0 in the y direction, and then s in the z direction, right? 0 on the x, 0 on the y, s on this. Then again, A, you've seen it before, s, 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 but what this now, when we find the EA position vector, we have s I hat plus s j hat plus 0 k hat. Right, so now we have two values, which just means it's going to take a little bit more work. Same thing though, we look EA. It's in the game, but what we do is we find the magnitude. So this is going to be the square root of s squared plus s squared, which is the square root of 2s squared. And this is multiplication, so you can simply take the s out. S square root of 2, right? And this is going to be, again, this is going to be equal to our r when we substitute it in. Then what we need to do is we need to find the unit vector of EA, right? And again, so what we do is we take our EA vector divided by the magnitude of EA, and we end up with s I hat plus s j hat over s square root of 2, which is easily just 1 over 2 I hat plus j hat. I'm sorry, 1 over square root of 2. Then we put it all together, right? So we have f of EA is equal to KE, again, q squared, because the q doesn't change. And then we have our r value, which is going to be s square root of 2 squared, quantity squared. And then now we just have to worry about the direction, so the unit vector. So what we can do is we can take this 1 over square root of 2 out of the I plus j and just put it right here. Maybe make it look a little cleaner. And then we have I plus j. And that's our f of EA. And in a similar vein to how we sort of did f of EA, or how we did f of DA and sort of looked at the ones that were similar, we can look at f of GA and see that it's going to be very similar. It's still sort of two axes, two, components. So f of GA, if we just start it out and we see G is going to be at S0, S0, 0, and then we have A at SSS. Then when we find our GA, we're going to end up with 0I plus S, J plus S, K. And we can see that we're going to have a very similar answer. All of the numbers are going to be the same, but it's just going to have a slightly different direction. So we can write our f of GA vector is equal to KEQ squared over R squared, which in this case is S square root of 2, quantity squared, times the square root of 2. And then now we just have to say, well, what axes are these acting on? It's going to be J and K. And then very lastly, there's one other point that we can do with the same technique on, and that's C, right? And we do f of CA, and I'm going to absolutely shock you when you find out that it's the same. KEQ squared over S square root of 2, quantity squared times the square root of 2. But then we just have to look at what axes it's going to act on, and it's going to be I and K, right? So I hat plus K hat, bang. So now we have 6 of our little things done. So we only have one more to worry about, and that is the origin, the one at the origin, which is now in 3 directions because our origin is at point 0, 0, 0, right? And then our A is still at point SSS. So now that we have 0, 0, 0 SSS, we take our OA, and we end up with our OA being SI hat plus S J hat plus S K hat. And then we do our magnitude, as we've done before. Oops. And we end up with S squared, the square root of 3S squared. This is S squared plus S squared plus S squared, 3S squared, which is S times the square root of 3. It's going to be equal to our R when we substitute it in. And then now we just need to find the unit vector, so the direction. So we're going to do OA over the magnitude of OA. You've done it before, with all of these, but now it's just a little more complex. But S I hat plus S J hat plus S K hat all over S square root of 3. So the S is going to cancel out, and it's going to end up with 1 over the square root of 3 IJK, right? Boom. So then, now we have everything we need. So we just come back and we put it into the equation. KE Q squared S square root of 3 quantity squared times square root of 3. And then we have I, J, K. And this is our vector f of the origin on point A. So now we have all of the vectors. Whew. That was annoying, but not too bad. Now we have all the vectors. Now the question is asking us for the magnitude. So since it's asking for the magnitude, what we have to do is we have to add up all of these vectors. And when you're adding up vectors, it's easy. You just add the i's to the other i's, the j's to the other j's, and you get a final answer in terms of I, J, and K. Now, that is very, annoying algebra and annoying adding. So I'm going to do a little bit of skipping, and that's where my all omnipotent tutoring powers come in, and I can look at the answer and tell you that what you're going to end up with is KE Q squared over S squared. And if you think about it, this is something that all of the different points have in common, right? And then big bracket. Okay, you're going to end up with K hat plus 1 over 2 root 2 I hat plus 1 over 2 root 2 J hat plus 1 over, plus I hat plus 1 over 2 root 2 J hat plus J hat plus 1 over 2 root 2 J hat plus 1 over 2 root 2 K hat plus 1 over 3 root 3 I hat plus 1 over 3 root 3 J hat plus 1 over 3 root 3 K hat. Whew. Whole lot of mods. But then, you add them all together. K E Q squared over S squared. And you end up with 1 over, oh my goodness, I'm going crazy. 1 over 3 root 3 plus 1 over square root of 2 plus 1 times ijk. I plus j plus k. And this sort of makes sense, right? Because it's a square. So each of the different, components are going to have the same sort of thing. But now you can plug in and you can get some answers. So this little thing in the bracket is roughly 1.9, so you can take that out, you can do all your answers, you can substitute in your Q value, your S value, and you get a final answer. But that's sort of, that becomes your resultant force, right? So this is your resultant force. And then what we have to do is we have to take we need the magnitude. That's what it's asking for, right? So we have our magnitude of FR, which is going to be equal to the square root of whatever number you have for I hat, for J hat, and for K hat. So in I hat plus in J hat plus in K hat. And these are all squared. And when you square the I, it goes away, but that's not really as important. So, and then you end up with your final answer for the magnitude. Whew. And yeah, then you get an answer. But yeah, this whole thing it's physics, but it's a lot of vector math. So again, we did the same technique for all of the different points. It's just that some were easy, they were in 1 dimension, some were in 3 dimensions, it was a little tough, and then a lot of, fraction and irrational adding. But that's how you go through this.